All right, so let's go ahead and get started. All right, so today's lab is on Jmpi instructions, but before we start with the topic related to today's lab, let me go ahead and save this first. There we go. So I'm going to go back to the previous lab, the lab that we did yesterday, just so that we can understand, what the questions are asking and what the correct answers are. So let me go back to that one first. I think it might be helpful for me to collapse some of these modules because I'm not really using it anymore. Not sure whether I can do that. Yep, there we go. Easy peasy. All right, so this is the lab from yesterday. So let's go ahead, let me go ahead and explain the answers. I'm tracking the text channel, so if you do have any questions, go ahead and ask in the text channel. All right, so the first question is the LD load instruction loads content from RAM to a register. The RAM location is specified by another register. The general format to use this is load X in parentheses Y, where X is a register A, B, C, or D, and Y is also a register A, B, C, or D. Note that X and Y can be the same register. Look up the opcode table and find out the actual binary opcode of the following mnemonic. LDCD, do not include any space. The answer should have exactly 8 bits. So that implies what base we are in, because a bit is a binary digit. So when I specify 8 bits, it is saying it should be a binary, which is also here, right? All right, so getting back to the opcode table, I need to look closer. There we go. All right, so we look up LD, and LD is up here. There we go. So this is the LD instruction. XX is the first register, YY is the second register, and the bit pattern is 0, 1, 1, 1, and then followed by XXYY. All right, so back to the question. So it should be 0, 1, 1, 1, and then XX in this case is needs to specify C, and C is the third register, which is represented by 1, 0 in hexadecimal. D is the fourth register, which is represented by 1, 1 in binary. So the entire opcode is 0, 1, 1, 1, 1, 0, 1, 1. All right, so that's the first question. Moving on to the second question. There we go. All right, so this is where things start to get a little bit confusing, partially because I switched my terminology from slice to location in the ROM. The reason why I used the word slice is because it's a slice of time. Because if you think about the locations in ROM, every single location specifies a discrete individual slice of time for the processor to do whatever it needs to do. So it's a quantum of time, because we cannot divide time any smaller compared to the duration of a single location in ROM. So that was partially why it was called a slice. But in the text channel from yesterday, I also explained what a slice is. It's basically a slice is a location in ROM. But in this case, we need to find the address. And the address is really just the opcode plus the 4 bits to the right-hand side that are all zeros. So state your answer in hexadecimal. So this time we have to use base 16. So the 0, 1, 1, 1 is a 7. And then 1, 0, 1, 1 is a B. And because we also need to specify the address in ROM, and we need to specify 1 additional 0, because that's what the splitter does before the opcode from the instruction register is merged into a 12-bit thing to update the microcode pointer. So I hope this one is clear why it is 7B0. And then on the third question, LD is a simple instruction. It is implemented by a single slice of microcode, which is basically a single location in ROM. So all the locations in ROM are microcode, and the single slice means a single location in ROM. look up the ROM of the processor and find out what is the first slice, first location of the microcode corresponding to LDCD instruction. State your answer in hexadecimal in all lowercase without the 0x prefix. Alright, so to answer this question, I need to use Logisim 2 because I cannot remember the 7-digit hexadecimal at that location. So what we do is we look up the ROM component, which is down here. Right click, go to edit content, and then we just have to look for that location 7B0. So 7B0 is right here. So you just need to copy and paste that particular value in. And I'm just going to put it here. So that value is, I'm just looking up 7B0, it's 1503056. So one is asking for the address, the other one is asking for the content at that particular address. And then question 4, the ST instruction has the mnemonic of STYX. In this case, the value of register X is copied to the RAM location pointed to by register Y. Again, X is one of the 4 registers, A, B, C, or D. Y is also one of the same 4 registers. How many variants are there to the ST instruction? In other words, how many ways can we combine registers for X and registers for Y? So the answer is 16 because there are 4 choices for Y, and then for each choice for Y there are 4 choices for X, and therefore it is 4 times 4, which is 16. And here's question number 5. The assembler accepts label definitions. This is a handy feature because otherwise the programmer will need to count the number of bytes used in code. A label definition is an identifier, same rules as a C variable name, followed immediately by a colon. A label definition must be the first name of a line, and there should be nothing other than comments after a label definition. So this is a label definition. Note that a label is a symbolic name of the address of the next byte. In other words, in the following code, L2 is the symbolic name of the address of the first byte of the LDI instruction. Assuming the above code is at the beginning of a program, what is the value represented by label L2? Alright, so there are several ways to answer this question. So up to this point, you don't really need to use the assembler, even though you have to use Logisim to look up the ROM location to find out what value it has. But we don't have to run any program. And for this one, you can, if you want to, use the assembler, but you don't have to. Because the LD instruction takes up 1 byte, because anything other than LDI, any instructions ending with an I, is going to take up only 1 byte. So this is only taking up 1 byte at location 0. This will start at location 1, which means L2 is a symbolic name of 1. So we just put a 1 here. In other words, L2 is not representing the content at that location. It is representing the address at that location. I'm still not seeing any questions, so I'm gonna continue and we move forward. Now we have question number 6. Labels can be used as an immediate value. This means LDI instruction can use a label as the I part. This is quite handy because very often we need to get the content from a specific location in memory, and labels make this easy. Observe the following code. When the program gets to the halt instruction, what is the value of the register B? Specify the answer as an 8-bit binary number. So for this one, you can just run the code. Okay. In other words, you copy and paste this directly into the assembler. Then you download the RAM file from the RAM file tab, and then you load it into RAM in Logisim, and just run it until the halt pin becomes 1. Then you can go ahead and inspect register B. So that's one way to do it. But the other way to do it is to understand what each instruction is doing, and then just do it without having to run the program in the simulator. So I'm going to do it the second way. All right, so let's count locations first. So in terms of locations, the LDI instruction is the only one that takes up 2 bytes. So byte 0 and byte 1 belong to the LDI instruction. Byte 2 belongs to the LD instruction. Byte 3 belongs to the halt instruction, and then byte 4 corresponds to the ST instruction. The first instruction, which is LDI A, L1, is going to load the address of the ST instruction into register A. So that means register A should end up with a value of 4 after the right after the LDI instruction. By the time we get to the LD instruction, A has a value of 4, B is uninitialized. So what the instruction is going to do is go to location 4, because register A is being used as a pointer to access the value at the location 4, which is the opcode of the ST instruction. That is going to be stored in register B. So register B should end up with the opcode of this instruction. Not 4, which is the location, but it should end up with the content at location 4. So if I were to look up the opcode table and hand assemble STAD, so let's look up ST, which is down here. So it's going to be F, 1111 is F. And then remember, this time XX, YY are reversed, and I think it's AD, if I remember correctly. Yep, it is AD. So register A is YY, which is the 00. Register D is 11, which is the XX. So we end up with 1111, 1100. So let's go back to here. And it wants a binary number. So that should be 1111, 1100. So I'm doing this by hand and not by using the simulator, but you are allowed to use the simulator to answer these questions. Then we move on to question number 7. In addition to specifying opcode translated from mnemonics, a program can also specify the value of a location using the byte directive. For example, the following code allocates and initializes 3 RAM locations to spell out tag in ASCII code. So if you look up the ASCII table, uppercase T is 84, lowercase a is 97, and then lowercase k is 107, and these are all decimal numbers. Currently, the assembler, okay, so that's my typo here, can only accept the use of base 10 unsigned integers, and only 1 byte can be defined per byte line. The byte directive can also be combined with the use of label definitions. This makes it easy to locate specific initialized RAM data, much like initialized global variables in C, C++. Note that a label is the symbolic name of a single RAM location. As such, in the following code, L3 is the symbolic name of the ASCII code of T. So this code is identical to this code here, except we have a label definition L3 right before the byte representing the T. Last but not least, the value of a byte directive can by itself also refer to a label, and this is actually possible. So what happens here is L4 is an address, but at that particular address, the content at that address is the address itself. That's what's going to happen when you have something like this, which is spelled out in the following sentence. This means the memory location is initialized with its own address. You can also write an entire program using the byte directive. Basically, you're going to have to assemble your own code and then convert everything into base 10. So this is actually a program. When this program cannot go any further, what is the value in register B? You may assume this code starts at location 0, specify your answer as a byte 10 integer. Alright, so this one is interesting because you can do it in 2 ways. Given that you're starting out with the opcodes, I'm assuming that you would probably go ahead and just run the code and find out what is in register B when this concludes. However, there's another way to do it, okay? And you can do it, okay? It's just a little bit difficult for you guys to do it at this point, but you can. So I'm going to show you how to do this, what is quote unquote the other way to do this. So this involves a process called disassembling, which is the reverse of assembling. So what we are doing here is I'm using a mouse pad, which is notepad here, to look at 100 and is it 89? No, 109, 109 in base 10, and I want to find out what in binary, okay, specifically in binary. So this is 64 plus 32, that makes up 96. Next one is going to be, let's see, 109 minus 96. There are no 16, so we can get an 8. Let's see. So that's 104. We have a 5 left. So we have a 4 and a 1 left. There we go. Hopefully I'm right, because if I'm wrong, it's not going to work out. So I'm going to have a 0. We have none of 128, 1 of 64, 1 of 32, none of 16, 1 of 8, 1 of 4, 0 of 2, and 1 of 1. So this is the base 2 representation. So now what we do is we look up in the opcode table and see which opcode can potentially have this pattern, which is a 0, 1, 1, 0, and then 1, 1, 0, 1. So let's look up the opcode table, which is here. So now we look up column A and look for 0, 1, 1, 0, and then 1, 1, something, something. So we can see, okay, let me pull the other window in so you can actually see what I'm talking about. Let's see, 0, 1, 1, 0, 1, 1, blah, blah, okay? That fits this particular pattern. So we're actually using an LDI instruction. The only part that we kind of have to figure out also is in here there's the placeholder of XX, but in here the placeholder has a value of 0, 1, which means we are loading something into register B. Okay, so now we know this is corresponding to LDI B, comma, and then the next byte, the byte right after the opcode of LDI, is the immediate constant. So in the question, that constant is L1 itself, so it is equivalent to LDIB and then L1. So now we will disassemble the next line of code, which is 117. 117 is 64 plus 32, and I think this time we have a 16. So how much are we dealing with here? So we have 80 plus 32, which is 112, and then we have a 4 and a 1, which is now translating to 0, 1, 1, 1. And then we have no 8, we have 1, 4, we have no 2, and then we have 1, 1 in base 2. This is how I do base conversion in my head. I just break the number down into powers of 2, so that I can express the original value as a sum of powers of 2, but each power can only appear up to once. And then we translate the presence and the absence of those powers of 2 and position those zeros and ones correctly, and we have the base 2 representation. Alright, so now we look up the opcode table of it again to see what opcode this is corresponding to. So we are looking for something that looks like 0, 1, 1, 1, and then 0, 1, 0, 1. And let's see, where is that? 0, 1, 1, 0. 0, 1, 1, 1, sorry, I misspoke. Right here. Oh, okay, it's the next line. Alright, so it's the next line, which is 0, 1, 1, 1, XXYY. So in this case, XX is corresponding to 0, 1, and YY is also corresponding to 0, 1. Different bits, but they're both 0, 1s, which means B and B. So the instruction is an LD instruction. So the next instruction in mnemonic form is LDB in parentheses B. And the next one is going to be the halt instruction because it is a 1. So that's just a halt instruction. So we have a halt instruction here. And then after the halt instruction, we have the definition of label L1, and it is just having L1 itself. So we do have to count bytes too, because let's see, we have 0, 1, 2, 3, and this is 4. So the label L1 is actually 4, but because we have a byte L1 here, we are also initializing that byte to be 4. So we can remember that. Okay, L1 is the same as 4. So as far as the assembler is concerned, whenever it sees the symbolic name of L1, it's going to say, oh, okay, you just mean 4. That's all. That's all the assembler is going to do in this case. All right, so now that we know what instructions are involved here, we can execute a program, and I can do it in my head. So the first instruction is going to load the value of label L1, which is 4, into register B. And then the second instruction will first utilize register B to go to location 4, because register B is specifying the address of where in RAM we want to go. So we go to location 4, which has a content of 4, and that is going to be loaded into register B. So register B would end up with a value of 4 in this case. All right, I'm going to submit, and you guys might want to see if you have any questions. All right, let me see if I answered the questions correctly, because if I did not, then I need to, I have some explaining to do, right? All right, so I think they're all correct. Yep, okay. So I will pause a little bit and, drink my coffee so that you guys have a chance to ask some questions. Oh, there we go. We have a question coming. Question number 2. Okay, so question number 2 is asking. Okay, okay, instead of me just repeating the question, let me see if I can find out what is not understood. So I'm going to read the question carefully. Startup logic sim, load, blah, 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 blah. What is the address of the first microcode slice? Okay, so is that part understood? I'm not. Okay, so that part is understood. All right. So the next part is to state your answer, which is the address of the first microcode. All right, so let me just double check and make sure. Okay, so microcode is referring to the ROM. A slice is referring to a single location in the ROM. And to implement means, it specifies the pathways between the components in the processor specifically to get this done. Okay, so those are the very specific meaning of these words in this context. So the question is, how do we find the address of the location in ROM that contains the bit pattern so that we can enable the registers, the RAM, and so on and so forth specifically to get this done? So the answer has to do with the decode cycle. So right after the decode cycle, that is when the microcode pointer contains the address of the ROM location to implement a specific instruction. So does that help answer the question? Now, if the next question is, but what is the decode cycle? I'm going to have to tell people to watch the video of yesterday and the video from last Thursday. Okay, the answer is no, it is not 000 because location 000 has nothing to do with LD. It does not change register C, it does not use register D, it has nothing to do with the LD instruction. There's a particular purpose to register to location 000 in ROM. It is the fetch cycle. Okay, when we have a rising edge when microcode pointer is 000, that is the fetch cycle. We talked about that last Thursday as well as yesterday. Alrighty. Though, it's probably not going to make any difference. It's really important to keep up with this class, reviewing the material and studying ahead of time, because we are compressed. As a 16-week class, this class is compressed already. So when we only have half the time, it is super compressed. So as a result, it is really super important to kind of review the material and make sure that all the concepts are understood, which means you can make a logical map of the concepts and understand how the concepts relate to each other. That's understanding, not memorizing, the words or the sentences. So, okay, I'm done nagging. Any other questions about this particular lab? Can I explain the 0 after the B again? That has to do with the splitter. So I don't want to re-explain things because this is going to take up a lot of time. So I can point you to where that was explained. And you probably know the answer already. It's in the lecture of last Thursday and yesterday. And specifically, the 0 has to do with what this thing is doing. This particular splitter is the reason why there's a 0. So I'm going to stop at that, okay? Because I really think that this has been explained enough times. It's a matter of just being able to go back and watch the video slowly and understand what I said when I explained it. All right. Because I have explained it twice already. Okay, so Folin is losing the stream, the YouTube stream, I'm assuming. Okay, yeah, it's going to be recorded. So even if it's stuttering a little bit, hopefully it's not enough to be problematic. I'm using the least minimum latency. Maybe it has something to do with it. Maybe not. I'm not sure. Okay, this is why I cannot wait until COVID is over so I can get back on campus. Then I can stutter, not the internet, but I can stutter at that in that case. All right, so that's it for the lab. So what we'll do today is the introduction of a few things that are important. I'm looking at the time. Maybe it's time to take roll now. And I wasn't as prepared as today. So I'm going to have to make the quiz right away. And it's going to be... We're almost done with the second module. In other words, we're almost ready to implement C code. Okay. Whenever I say C code, someone is going to say, but I don't know C code. I learned C++. So I'm going to say, we're going to translate C++ code into assembly. So we're going to add a quiz. And that's going to be 2021-0707. Row taking. And I'm still thinking about what word I am going to use. I think I got it. I'm just going to be lazy here. What is the word? Fill in the blanks. and it is going to be JXI. So JXI or lowercase. So I'm going to say JXI. There we go. And make sure it is fill in the blanks. Yep. Update question. And go back to give you guys 5 minutes to answer this. So I'll make it due at 6:07. So July 7th, 6:07 p.m. All right. Save and publish. There we go. So just copy and paste from the text channel. JXI is the word. That's a very good question. The lab today has everything to do with JXI. So yes, we will have a lab today, and in today's lab we'll learn about how to trace a program written in assembly. And also, in today's lecture, I'm going to show you guys how conditional branch and unconditional branch are implemented. All right. I'm just going to take a quick peek and see how many people are done with this row taking. And if most people are done, I am going to move forward. Yep, I see most people are done. Okay, so alright. Alright, so we're going to move forward. So moving forward, I'm going to go back to the opcode table. And this time I'm going to I'll explain the Jmpi instruction first. So this is the Jmpi instruction. The opcode is very simple. This time there are no XX and no YY because it doesn't use registers. So this instruction does not use any registers, and therefore it is just a quote-unquote constant. But when you look at column C, it looks really kind of weird, right? Because it says PC equals to asterisk PC. So we are dereferencing PC. Okay, use PC as a pointer, go to that location, retrieve the byte at that location, and then use that to update PC itself. That is what the implementation looks like. Well, let's see what this is going to do. Okay, so we're going to write a very simple program, and this time I'm going to use the assembler, so that I can repeat the process of how to use the assembler, just in case some of you might have forgotten how to use the assembler. So I'm going to go to a tab with the assembler, which is this one. Go to source, and I can erase a good portion of this, which is not needed. And I'll put a no op instruction here, just so that we're not Jmpi, going back to the same location. So we have at least so that we can actually see the alternating between these two locations. And then we have a Jmpi instruction. Jmpi, and what goes after the Jmpi instruction is going to be a value. That value is the address of where to continue execution after the Jmpi instruction. So if I want to go back to the no op instruction, which is at location 0, I just have to specify 0 here. Now it is better to use labels, but I don't have to. So this will work, and we're going to go to the RAM file tab. And remember, when you are downloading, you have to be in this tab, otherwise it's not going to work. So we download as CSV. TSV will work too, but I just personally prefer to save it as a CSV file. And you can save it to any place you remember, you remember where to find it. So I'm just going to put this in my temp folder as jmpi.csv, like so. And then switch back to the simulator, which is right here. All right, so this time I can actually go ahead and reset simulation, because the content of RAM can reset because I have a new program to load into RAM. So right click here, go to load image, And then we have to go all the way back to where I placed the file, which is /tmp/ jmpi.csv. All right, and this is the entire program. So byte 0, the 00 at byte 0 is no op. And then the next byte, which is 40, is the opcode corresponding to the Jmpi instruction. This one here is the immediate value corresponding to the Jmpi instruction, but it is not an opcode by itself. It is just something that the opcode needs in order to do its job. All right, so let's go ahead and find out what is going to happen when we Control T through this code here. And just so that we have another exposure of the fetch cycle, here we go. Microcode pointer at 0, 0, 0. We're going to have a rising edge transition. It is called the fetch cycle because whatever the program counter is pointing to is going to be loaded into the content of the byte that the program counter is pointing to is going to load into the instruction register in this case. So here's Control T, and you guys go like, oh, okay, where's Control T? I thought I did a Control T. There we go. And and you guys would go like, but nothing changed. Well, that's because the content at location 0, 0 is also 0, 0. So you would not be able to see the change because, hey, the new value is the same as the old value. Control T again, the microcode pointer should increment. And then Control T, again, the program counter should increment. So I'm not explaining why those things are happening because those have been explained twice already. Again, once yesterday and once last Thursday. And then when we Control T again, this one you might want to take some notes of. Remember, every single time I said you might want to do blah blah blah, it usually translates to if you don't, it's gonna hurt. But it is your choice. Okay, so when the microcode pointer is 0, 0, 1 and you have a falling edge, that is the decode cycle. Okay, so here we go. I'm just re-explaining what is the decode cycle. Control T, and now we're back to location 0, 0, 0. So the decode is going back to location 0, 0, 0 because the opcode is 0, 0. After we add a 0 to it, it goes back to location 0, 0, 0. This is why the no-op instruction doesn't do a single thing, because all it does is to increment the program counter and then go back and say, oh, I'm ready to fetch the next opcode. That is why the no-op instruction doesn't do a single thing. All right, so what are we going to do now? Because we are now ready to fetch again. But how do we know we're ready to fetch again? The microcode pointer is at 0, 0, 0, and the next transition is a rising edge. That is how we know. So the next fetch is going to grab 40 into the instruction register. That is the fetch cycle. So observe the instruction register, Control T, and it is now 40. The falling edge is going to increment the microcode pointer to 0, 0, 1. And then the rising edge is going to update the program counter. So the program counter becomes 0, 2. Now, this is critical. Okay, this is really, really important because right now the program counter is pointing to the opcode of the Jmpi instruction, which is the 40. Now, it's not highlighting because RAM is not selected. Okay, that's the only reason why it's not highlighting. But the program counter has a value of 0, 1 right now. So the increment, which is about to happen, is going to cause the program counter to become 0, 1. When the program counter is 0, 1, it's going to point to the byte right after the opcode of the Jmpi instruction. So this is why it is important to remember when to increment the program counter, because it has to get past the opcode to get to the byte that supplies additional information to the opcode. So Control T, you can see how the program counter is updated to 0, 2. And then the falling edge, okay, now that we have microcode pointer being 0, 0, 1, the falling edge is once again decode. And the decode is going to update the microcode pointer to 4, 0, 0 in this case. and whatever is at that location in ROM is going to specify the pathway that is specific to the Jmpi instruction. Alright, so there's some traffic in the text channel. I'm just looking at the text channel and go like, I'll do that after the class is over. And then we have I'll do it after the class is over. I'll consider doing it after the class is over. There we go. Okay, so getting back to this. So Control T, we are now at location 400, and this is the bit pattern that specifies how the Jmpi instruction is going to work. So we already know the Jmpi instruction, according to column C of the opcode table, is going to use the program counter to point to a location in RAM, use whatever content is at that location to update the program counter itself. We already know that from reading column C, so now we can just kind of do a fast forward to verify that that is the case. First of all, RAM is selected because we are going to read a location in RAM, and we can also confirm that RAM is getting read because the load pin or the load port has a 1. So we are indeed reading a RAM location. Now we want to track down who is driving the address port or who is specifying the content on this particular node. And it goes, it's coming from a multiplexer. This multiplexer has a 1 for the select, and we look up input 1, and input 1 is coming from the program counter. So this is how we can confirm that the program counter is indeed acting as the pointer, pointing to the location in RAM where we're going to grab a byte. So now we have to track down the output of RAM, which is from the data port. So the data port goes to a whole lot of places, and we just want to confirm that this eventually ends up in PC because we can see how the program counter is already enabled. So it is. So we just have to find out whether this wire from here is going to connect to here. So we'll do it one step at a time. This is coming from the output of this multiplexer, which has a select of 1. So indeed, we are using this particular input to feed the output. So it is at least going to the right multiplexer. Now with this particular multiplexer, this output is connected to the select pin is a 1, so it's coming from input 1, which is indeed this wire. So now we have confirmed that whatever the data port is outputting from RAM is eventually going back to the data port of the program counter. And since the program counter is enabled already, so at the rising edge, the program counter will be updated by the content that the program counter itself is pointing to right now, which is 00. So let's go ahead and do the rising edge, and we should see the PC becoming 00 in this case. So Control T, and it becomes 00. Now we have a falling edge, but since the microcode is already done, so the transition it will go to location 401. It's just that it will only be there for a short amount of time that we cannot see. Instead, we'll see that it goes straight to location 00, and now we're ready to fetch the next opcode. But since the program counter is back to location 00, that means we're stuck in an infinite loop. All right. So that's how this program works. Okay, it just alternates between those two instructions. And if you want to see that animated, it's actually pretty fun to do. Just go to tick frequency, pick something that you can see. 32 Hertz will work, and then go to simulate and turn on ticks. Okay, click on ticks enabled, and now you can see how it is just alternating between these 3 locations. So that's the unconditional jump instruction, the Jmpi instruction, which is equivalent to the statement, the goto statement in C++. All right, and let's see. Let me look at the time. It's 15. Okay. All right. So now we want to look at conditional branch. So conditional branches are extremely important because that is the only way for a program to make decisions. In other words, if you have conditional branches, loops, where you need to say, okay, is it time to get out of the loop? Should I exit the loop or should I continue in the loop? All of those are decision makings. And even though in C++, the decision making are based on conditions like comparison, logical and, logical or, logical not, and so on, in assembly language, everything boils down to whether a flag has a 1 or 0. Yep. So the question is, how is it implemented in the processor? But before we look into that, let's look into the opcode first. So there are 5 opcodes corresponding to conditional branches that we're going to use in this class. There are more than that, but the other 5 we do not use. So these 5 instructions here, which is starting with JLI and then JOI, JSI, JCI, and JZI, these are the conditional branches. And the column C is indicating how they are implemented. So if you look at column C, let me just magnify a little bit. There we go. So when you look at column C, it is a ternary operator or ternary expression. And all that is saying is, in this, I'm just going to use JLI as an example because all of the other ones are almost the same, exactly the same, except they look at different flags. So for the JLI, it is asking if the L flag is true, then the expression is going to return whatever PC is dereferencing to. In other words, what is the value at the location that the program counter is pointing to. If L is false, it is going to return PC plus 1. Effectively, it is just incrementing the program counter if L is false. If L is true, then it's going to the program counter is going to be updated by the content in RAM that the program counter itself is pointing to. So it is basically saying, it is almost exactly like a Jmpi instruction, except it is conditional. If the L flag is a 0, it will be just like, it will behave like a no op. If the L flag is a 1, then it behaves like a Jmpi instruction. I think that's the best way to put it. Okay, so JLI is behaving like no op if the L flag is a 0, and it behaves like a Jmpi instruction if the L flag is a 1. All right. So let's go ahead and find out how this is implemented. This is actually quite fun, how this is actually implemented. So at this point, okay, I'm just going to say this. At this point, to study is really just to understand how the opcodes are implemented by microcode. And you should have enough knowledge to figure out all of that stuff at this point. Okay, I'm not requiring you guys to come up with the microcode of something that I want to implement using this processor architecture. So your job is to figure out, how the microcode in ROM is turning on, turning off, switching the multiplexers and demultiplexers in order to get a specific job done. All right, so let's go ahead and find out, how to test this code here. The opcode is a 4-1 in this case. So I'm just going to inject this code into Logisim. And where's Logisim? Logisim is right here. There we go. We want to make sure the clock is a 0 before I reset. Well, actually, I can reset the whole thing because I can inject the entire program in. So we'll reset simulation. And I think I disabled. Oh, I turned off the wrong thing. There we go. All right, now it's all good. And now we are going to specify the code. So I said 4-1, and we wanted to. So the next question is, where do we want it to go if the L flag is a 1? I'm just going to pick some location here. Let's jump to location 80. If and only if the L flag is a 1. Otherwise, we continue execution at location 2. So that's what this program is going to do. And let's go ahead and run that code. So we're gonna kind of fast track through the fetch cycle. and also the decode cycle. And now we're at location 410. So whatever bit pattern is at this location, that particular bit pattern is going to control the components inside the processor to get the conditional branch done. So the first thing we want to do is to check the flags register and see what content it has. You can look into the flag register like this. You can also look at it through the output pin. They're all zeros, which means the L flag is also going to be a 0. So now we want to find out, okay, but how does it work? The first thing is to track down what is going to be updated. We can see RAM is addressed, but it's a read operation. And then we can also see the program counter is enabled, because after all, the program counter will be updated one way or another. Okay, either it increments, which means it behaves like a no-op instruction, or it will update to the content that the program counter itself is pointing to right now, which is the same thing as a Jmpi instruction. So now we want to see what's going to happen here. By tracking backwards, okay, we're tracking the D port. It's coming from this multiplexer here. Now before, we just say, oh, it's a 0 or it's a 1, but this time we want to find out why it is a 0. So PCMux, as it turns out, is not coming from the ROM directly. It is a tunnel that is up here. This is the PCMux tunnel. So what determines the value of PCMux is this particular multiplexer here. This multiplexer has a select wire that connects to PCMux because it's a multiplexer to a multiplexer. So, well, okay, the value is used to select an input from a multiplexer, but the output of this multiplexer goes into the select of another multiplexer. So that's why it's called a PCMux. Okay, it's just me making fun of the control signal. So PCMux does come from ROM, and we can confirm that by looking at which wire is highlighted, which is this one here. It's coming from Ucode data. Ucode data itself is coming from the output of the ROM. So what is it doing? It is 100, which is telling this multiplexer to use input 4 to hook up to the output pin here. This is input 0, 1, 2, 3, 4. This is 4. And this turns out to be bit 4 of the flags register, which is also the L flag. Then you go like, but how do we know bit 4 of the flags register is the L flag? Because tag, if you don't document this, how do we know? Well, guess what? I have already documented it in the form of the logic sim circuit. So the way we do this is we track down the D port here. It's coming from the ALU. Then we look up the ALU. We look up the flag's output, which is this one here. We look up bit 4. This is bit 4. Bit 4 is the output of the exclusive OR between the sign and the overflow. That is how we use LogicSim or the processor circuit file as a self-documenting design so that you can track down how things are done. And all I have to do is to give you the file. I mean, once I explain, how a merger work, once I explain how an exclusive OR work, you should be able to track this down yourself and be able to find out what I just illustrated. All right, so getting back to here. So that means this mechanism here is basically using one of the 5 flags to select the multiplexer to help this multiplexer select which input connects to the output. If it is a 0, it simply increments because it connects to the increment mechanism. If it is a 1, it connects to this multiplexer, which then connects to this port here, which then connects to the data port of RAM. That is how it can do the conditional branch by controlling this multiplexer here. So the next question is, but Tech, I'm not really, now that we know that it behaves like a no-op, it just increments the program counter, can we see what happens when the L flag is a 1? I'm glad you asked. because we can now inject a 1 into the flags register. At this point, the processor has paused. Okay, time has stopped for the processor. It's kind of like being at a breakpoint when you're debugging a program in C++. So at this point, we can change the value of registers so that we can actually kind of play out different scenarios. So we want bit 4 to be a 1. Bit 0, 1, 2, 3 belong to one hexadecimal digit, and then bit 4 is the least significant bit of the next hexadecimal digit. So to specify bit 4 being a 1 and all other flags remaining as zeros, we have to use 10 in hexadecimal. So 10, there we go. And you can see right away bit 4 coming into this multiplexer becomes light green, and that in return becomes PCMux. So PCMux being a 1 means this particular multiplexer will select input 1 to update the program counter, and that in return goes to this multiplexer, which then return goes to the data port of RAM, which means in this case, if the L flag is a 1, then the program counter is going to update to 80 in this case. And I can just poke the wire to let you know. See how this is 80? It's about to update the program counter to 80. So I'm done with this demonstration because there's no point in actually carrying out this operation because we know that it's just going to continue execution at location 80. All right. So I have just talked about a lot of stuff, okay? But everything hinges on how things are connected within the processor and also the operation of multiplexers. So if you understand multiplexers, registers, RAM, the various computing elements inside the ALU, you can track all of this down. Okay? In other words, you can figure out how a single slice of microcode get things done in this processor. And that particular knowledge, being able to figure out these things, is not optional. The next exam, your exam 2, is going to have questions that will require your understanding of how the processor works. So I would encourage you guys to do what I just did. Okay, use maybe with another instruction, but it's really kind of important to get through this process so that you understand how to track things down and understand how the ROM is configuring the multiplexers, demultiplexers, registers, RAM, and decoder in order to form the correct pathways and have the right components enabled to get things done. I know it is tedious. I understand that, but that is what you need to do to gain a better understanding of how a processor works. All right, so I'm going to shut up a little bit here and see if you guys have any questions. I am not seeing any questions. All right, so the next part of this lecture is going to show you guys, a few features in Logisim. So if you're going to debug a program in Logisim, using this particular processor architecture, it can get very tedious. Okay, if your program misbehaves, how do you know your program has misbehaved? So the idea is to use a tracing or a logging mechanism that is built into Logisim. So with this particular program, well, this is not a bad program to track. So what we'll do is we are going to continue the execution of this program, but I'm going to enable logging first. To enable logging, you don't have to write this down because I know I'm going to talk pretty fast, but the instruction is in the lab already, so you don't have to write this down. You might want to jot down the time, like 6:30, just so that, if you need to refer back to the lecture, you know what time to refer back to. So I guess, 31 would be more appropriate. So to turn on logging, you go to Simulate, you go to Logging, And once you get there, you will see something like this. I did some logging earlier, and that's why I got some junk here. So there are two ways to log. Okay, either way of logging requires you to specify what you're logging. So on the left hand side here are all the things that you can log, and on the right hand side here are the things that you are currently logging. So you just have to select whatever you want here, click add, and it will appear on the other side. So the question is, what should you be logging? Whenever one of the things that you're logging has changed, it will create an entry either in a table or in a file. Okay, and I'll talk about that in just a little bit. But a log entry is triggered by a change. So if you pick something like clock, okay, if you pick this one, you're going to end up with a lot of log entries because the clock ticks, you know, the clock is the most frequently changed signal, so you'll end up with a lot of log entries. Is it going to be helpful? Probably not. Okay, you can log the address port of RAM, but that by itself may not be very useful because it doesn't know whether you are fetching or you have an instruction that is reading a byte as data from RAM. So it would just get updated, all the time. So one thing I would consider logging, not only for tonight's lab, but also in the future when you're debugging your program, is to pick one of these two. They are the same. There's no difference between these two. This is the register, and this is the output of the register. They're basically essentially the same thing. So I'm going to add this. Okay, so as soon as you add it, you can see that it is now in base 2. You can click on change radix in order to change it to base 10 or base 16. Personally, I would use base 16 because the assembler uses base 16 in the assemble tab. All right, so let's see. So let's just use the program counter. Okay, there is another thing that you can log to, which is the fetch, op fetch. So this pin is a 1 if and only if we're dealing with a fetch cycle, which can be useful because you can now differentiate between the program counter is getting changed because of some reason, as opposed to the program counter is being used to fetch an opcode. Okay, so might be useful to combine these two. I'm going to add that too. There we go. Okay, so and you can add as much stuff you want to add into here. So once you're done selecting what you want to log, I personally prefer not to use a table. So every time you change the selection, the table is gonna reset. But I personally would log things to a file. Now the question is why? The reason is the table can only keep track of the last 400 entries, whereas the file can keep track of basically, it's up to the capacity of your hard drive. And I know you guys have terabyte hard drives now, so I know there's plenty of space. So if you want to log it to a file, all you have to do is to select the file first, because otherwise enable is grayed out, you cannot enable it. Include headline is useful, so keep it checked, and then you just have to find a place to put your log file. So I'm going to put it in temp, and this is JLI.tsv. Okay, this is a tab separated value file, so instead of using a CSV, I'm using TSV. Click save, and you can now see that it is automatically enabled. If you click this, it's going to disable it. So at this point, it's already set up, and we can close the window, and we can enable the auto ticking. So we go to tick enabled, click on it, let it go for a little bit, and then stop it. There we go. So now I'm going to open the file using a terminal, and let me find my large font terminal. Where is it? It's the last entry, of course. There we go. Oh, it's not even that one. All right. So where's my I lost my large font text terminal. that's okay. We can always redo it like that. All right, so I'm going to the folder and looking at the jli.tsv file. Notepad can open this too. It's a tab separated value file. You can also use a spreadsheet program to open it. So you can see how the program counter is staying at 880 and then up fetch. So that means this entry is indicating we are fetching an opcode at location 80. We are now fetching an opcode from location 81, 82, 83, and so on, because guess what? Those are all zeros. In other words, they're all no ops, and that's why we just have a sequential operation, um, that's why the program is executing sequentially. That's probably the best way to put it. So Control F, fast forward, and I didn't really give it a whole lot of cycles, because by the time we get to location FF, it's going to wrap around to location 00. But because the L flag is still a 1, nothing in this program is going to change that flag back to 0. So after location 00, it's going to go back to location 80, because the conditional branch is going to branch to location 80. So this is how you can track the program. Now, if you want to say, I have just done some changes to the program and I want to restart the tracing. In other words, I don't want to keep the content of what is in the TSV file at this point. You got a few choices to do that. The best way to do it is to go back to Simulate, go to Logging again, and then go to File again, and then go to Select again. Now, when you go to select again, you can actually reuse the same file. You can see how I'm reusing or respecifying jli.tsv. And the moment you click save, it will tell you that this file already exists. So at this point, you have two options. The program will ask you, which one do you want? Generally speaking, you want to overwrite, because otherwise it would be very difficult to differentiate the log from the first run of this program versus the run from the second versus the log from the second run of this program. So if you click overwrite, it's going to erase the file first and then start from scratch. So keep this in mind, because one of the questions in your lab today might need something like this. Now, the other thing you can do is to specify a different file. So if you say, okay, I don't want to run into any risk of potentially appending to a file that is already here, you put it into a different file. So now I specify jli1.tsv because it is a new file. There's no way that I will be appending the log of this second run of the program to the same file. So you definitely have the choice, okay, of how to do this. For the lab, I would just basically say don't use the table, because the table is there's no way to reset the table. That's the problem. In order to reset the table, you will have to make some changes to what you're logging. So you have to remove something, and then when you go back to table, it just removes the column. Okay, so you have to remove everything from what you're logging. That will clear the table, because now the table has no columns, and then you reselect things back into what you want to log, which is a lot of trouble. Okay, so my recommendation is for tonight's lab, just use files, not a single one. Use one file per case that you have to track. Okay, I'm not going to tell you, what you're tracking, but the instruction of the lab would say that. All right, so there's that. So I'm going to pause and see if there are any questions.
Yeah, I was curious why the location in the log file gets referenced, the same location gets referenced 3 times over.
Yeah, I was curious why the
We can experience time loop here, and also delayed answer, because by the time I hear your question, it's already 6 seconds past your time of asking that question. So the reason why we are seeing, let me go back to the log file first so that we can talk about that. I just passed it. There we go. Okay, so Oh, because I re-specified the file. Okay, so each row is representing a change. So the OP fetch was a 0 and then became a 1. So that change from 0 to 1 causes an entry to be logged. And then when it switches back to 0, when OP fetch goes back to 0, that is why we have a second entry. And then when the program counter increments, that's also a change of one of the at least one of the things that we are logging, and that creates another entry and so on. So does that kind of explain, why we seem to have duplicate entries? Because if you compare all those rows, no two adjacent rows should be the same, because it has got to be something has changed to trigger another row to be created in the log. So it could be the OP fetch, it could also be the program counter in our case, because those were the two things that we were tracking earlier. And you can also look into the circuit to find out what OP fetch really means. So this is the halt flag. The halt flag is a 1 if and only if the content of ROM that is driving the output are all zeros. So that's how we identify that we are at a halt instruction. And then OP fetch is, where is it? Right here. So OP fetch is right here as an output pin. It is the result of an AND between clock and also the enable of the instruction register. So that means it has significance because it is gonna it will record right at the moment or shortly after the transition from after a rising edge. And as a result, if you look at the instruction register, when OP fetch is a 1, that is the opcode that we just fetched. If you look at the program counter when OP fetch is a 1, that reflects the address of the opcode that we just fetched. So that's why OP fetch has a significance, because it would be a 1 if and only if we are in the fetch cycle. All right. Any other questions? No additional questions. Wow. Okay. So without any additional questions, I am going to... Okay, so let me just kind of ask another question to the class. Maybe it's not a question. If you find that you cannot understand how the content of ROM is controlling the connectivity, and also which component is enabled, how they're connected in the processor, the first thing I would recommend you to do is to make sure that you understand each and every type of components. So we don't really have a whole lot of types of components. Let me point out what type of components we have here. And this is inclusive. This is including everything. This is a clock pin. The clock pin is something where you can turn on auto clock to make the program go by itself, or every time you click on it, it just toggles. This is a button, which is normally a 0. When you click on it, it becomes a 1. This is a not NAND gate. This is an AND gate. AND gate. These are tunnels, output pin, output pins. This is a multiplexer. So you might, if you don't understand what a multiplexer is doing, we have a problem, because we have been using multiplexers and I've been using it to explain the operation of the processor. It's basically a switch. You have multiple inputs, one single output, and then the select, which is the one going into the gray dot thing here, is going to control which input is going to drive the output. It might have an enable. If it has an enable, that means if the enable is a 0, nothing is connected to the output. When the enable is a 1, then whatever the select is specifying would connect the input to the output. That's a multiplexer. A demultiplexer is exactly the opposite. Single input, multiple output, have a select pin to specify which output connects to the input, but it also has an enable sometimes. And if the enable is a 0, then all outputs will be zeros. If the enable is a 1, then only the selected output connects to the input, and it depends on whatever the input is in that case. Inside the register bank, we have a decoder. The decoder is kind of like a single bit demultiplexer having the input connected to a constant of 1. That is basically what a decoder does. We got registers. Okay, so registers we have talked about for a not long time already. And let's see, what else do we have here? Oh, we got ROM. Okay, so ROM is basically just a table. The A port is kind of like the index. If you want to look at the content of ROM as an array, then the A port is what you specify inside the square brackets, which is the index, and D port is the content at the location that you addressed. So you either look at the A port as dereferencing. Okay, you specify the address and it will dereference to the content, and then the output is the value at the location. Or you can look at the ROM as an array. And then we also talked about RAM. So with RAM, it is kind of like ROM, except it's more flexible because we can update the content in RAM. That's why it has a load pin and also has a clear pin. And it has a clock pin too. The clock pin is only used when we need to update the content of RAM. So that's pretty much it. Okay, the only thing that I haven't really quite fully explained yet are these individual things that the ALU can do. This is an adder, this is a subtractor. For the most part right now, we just need to understand these two. This is a right shift, this is a bitwise NOT, this is a bitwise AND, and this is a bitwise OR. And then we have AND OR gate to implement the two overflow. This circuit here is computing the overflow for addition. This one here is computing the overflow for subtraction. So if you work out the math, you should be able to match the circuit here with the overflow equations or expressions for addition and also for subtraction here. And that's it. I mean, if you think about the components that are being used, okay, fine, we have an exclusive OR here too. So if you just look at the components, those are all the components. The rest is really just about how the components are connected. You're not going to be asked how to make new connections between the components. You just have to understand how they are currently connected and how the content in the ROM is going to control these components so that the components end up doing what they are supposed to do. And what they're supposed to do is documented in the opcode table. So that's kind of the quick rundown of what I think you guys should be able to do is to use the processor circuit diagram as a self-documenting mechanism or self-documenting design to understand how these operations are performed. All right. Any questions? If there are no questions, I'm going to open up the lab for tonight. Alright, so the lab tonight is called Simple Branching and Code Analysis. And just remember, the lab itself also contains instructions and also information and knowledge. So if you think you might want to make a copy of this, you can go ahead and copy and paste the quiz into a word processor, or do whatever you need to do to screenshot it. The quiz access code is JXI, so I'm gonna put it here. So we're going to use JXI also as the access code of the lab. And I'm going to give you guys until the usual time. So July 7th, 8:20 p.m. Here we go. Save and publish. Alright, so the lab is released. The access code to the lab is in the text channel. So you can click on that. Just copy and paste it into the lab activity. And that's it. So I'm gonna stay on for another maybe 10 seconds, just in case somebody has a question. All right, no questions. I'm gonna stop streaming and get out of the voice channel. I'll be back in about 10 minutes. So if you have questions about the lab, I will start to answer questions in